Today, I'm going to talk about uh, how we can look at molecular structure of a molecule and predict what it smells like. So we know in vision audition how to do this. So if you look at this example on the screen, when you look at color vision, we know that the key axis to determine color is wavelength. We know for sound, it's frequency. We know the barriers of perception. So we know that the visible wavelength ranges between 400 and 700 approximately, and auditory range is from 20 to 20,000 hertz. In addition, we've constructed maps, perceptual space that predict how you can mix these sort of elemental stimuli together to make complex mixtures. So you can mix red and green lights to make a yellow light, and you can mix different sounds together to make major and minor chords. In addition, you have devices where you can measure these physical properties and predict perception. So this is a colorimeter. So you can look at a color and predict what color people will perceive it as. This is a spectrum analyzer for audio waveforms. However, in olfaction, we don't have an instrument. We have instruments that can measure physical properties, but we don't have instruments that reliably predict perceptual properties. So currently, the gold standard in the field is still a human sensory panel, which is both expensive and time consuming. So why do we still use sensory panels instead of instruments? It's because we don't really understand the precise mapping from structure to percept. So we have lots of cases where two molecules have similar structure, but different percept, or have different structures and similar percept. And some of the most striking examples are these triplets from Charles Sell's 2006 paper, where two molecules here are structurally very similar and two molecules are perceptually very similar, but they're not the same two molecules. Here's another one. These two molecules have exactly the same atoms. One is just straight chain and one is branched. However, the two on the right are the ones that smell most similar. So what this indicates is that our map from molecular structure to perception is not really adequate given the current techniques that we're using. So how can we find a better way to numerically represent odors? So one way is to, that we try to attack this, is to use neural networks. In a sort of traditional neural network, you feed in numerical features. So for example, you can measure the molecular weight, whether or not a molecule has a specific functional group like an ester, and how hydrophobic or hydrophilic a molecule is. These numerical values get recombined in the neural network. So to form an additional set of features that are then used to predict the output. In this case, it will be odor descriptor labels. So you give a molecular structure and try to predict which label applies to it. So you can imagine that some of these middle nodes might do things like combine molecular weight and hydrophobicity to determine if a molecule is able to be smelled, right? Is it volatile enough to reach the nose and hydrophobic enough to enter the olfactory receptor? And so you have a node that sort of combines these elemental features into something new. And then if you wanted to predict fruity, you have to both know whether it's an odor and whether it's fruity. So we use a slightly different type of neural network to do this. This is a graph neural network. And the reason we use this is that it's really been shown to outperform other algorithms in chemistry applications. So for example, antibiotic discovery or photovoltaics or cancer therapeutics to predict new molecules. So this is a slightly different form of input where you're representing the information in a graph format. Eventually, right, you exchange information between different nodes in this graph and again, get back to numbers. So there's a slightly different transformation here, but you end up back at the same neural network. And what's nice about all these different neural networks is that they produce some sort of intermediate representation of odors. So rather than just having molecular weight and functional groups, you have this sort of new representation that we can use to create a new space. And the goal here is to create a space where we no longer have these jumps where things that look that are close to each other in this space are perceptually very different from each other. So these graph neural networks have outperformed previous methods. So this is on the x-axis, the state of the art, the model designed for dream olfaction challenge that was designed to predict correlation. Here we sort of repurposed it to predict whether a label applies to a molecule. So whether a molecule smells grassy or fruity or fatty. this is the unit slope line. So points that fall above the line suggest that the new method, this graph neural network, is better. And points that fall below the line suggest that the baseline method is better. And so now we can look at each label and see how well this label performs. So this is a set of about 5,000 molecules from a Goodsense company and a Leffingwell database. And we can see that the graph neural network outperforms the baseline model on almost all labels, and especially labels where we have more data. So that's great that this model works compared to a previous method, but that was based on sort of a static data set. And what we would like to do is really design a stringent test for this model. So the best test is a prospective validation. We want to select molecules that are not in flavor fragrance catalogs. We want to predict what new molecules that nobody has ever smelled before smell like. And so we took a catalog of molecules from a drug screening library. We filtered it using various criteria, such as weight and charge, price, toxicity, so we can test them in human panels. And from this pool, we selected 400 of them to test double-blind in humans. And these were designed to be spread out in the space. You can see we had a lot of room to maneuver here to pick the 400. We tried to spread them out so that we don't just have molecules that are close to our training set. Again, we're trying to stringently test this model to see how well it can do as prediction. So here's, just to take a step back, what the training data look like from Leffingwell and Goodsense. So you have a molecule and you have some labels just as a word in a database. So this particular molecule, L-carvone, smells sweet, spearmint, herbal, and minty, and that's all the data you get for it. It's hard to reproduce this data ourselves because this was collected, the methods for collecting this are not totally clear. Expert labelers contributed, but we don't know how many labelers there were or exactly what methods they used to produce these data sets. So we use a slightly different method than the training data to form our validation data. So we trained panelists using a lexicon of 55 odor labels. We gave them a reference kit. So every time we tell them to rate green, they have a vial which will tell them what we mean when we write the label green. And then they would also get different examples for other words like grassy, cucumber, and tomato that sort of fall under this green umbrella. And so for each of the 400 molecules, at least 15 panelists rated how well these 55 words, these labels applied to a specific odor. We again can sort of compare to test-retest here on the y-axis, compared to the sort of gold standard data set for this from the Dream Olfaction Challenge. They had 49 people rate 21 descriptors, and you can see the test-retest values here. Here we have many fewer subjects, about a third as many subjects, and yet we're still getting really good test-retest at the group mean level. Some labels, for example, we couldn't improve on, so the label garlic was used very reliably by subjects in the Dream Olfaction Challenge, was also used reliably in our data set. Other labels, for example, grass, were used relatively inconsistently in the Dream data set, and were used much more consistently in our data set. So now we take this molecule and our data look a little bit different. So this is the same molecule in our data. So this is a radar chart with all 55 labels here. And you can see here that indeed the same molecule was labeled as mint, herbal, and sweet in this particular representation. So this matches up relatively well to the draining data set, even though the format is a little different and now we have these numerical ratings. So now how do we compare our model predictions to what the human panelists are saying about what things smell like? So we know that when people smell things, as Mackenzie pointed out, their perception can be variable, both in the way they actually perceive odors and the way they describe their odors. But we also know that there's a central tendency and consensus for description of stimuli. And so if you get a large panel together to rate these, one large panel looks very much like another large panel, even though individuals within those panels are different from each other. So for example, if you give this molecule to subjects, some will smell it and say that it is fruity and sweet. Another might say that it's floral and powdery, and a third might say that it's floral and sweet. And so if we take the mean of this panel, the consensus is that this molecule smells floral and sweet. And so what we're trying to predict is not what the individuals are saying, but what the panel is saying. And what we want to do is measure how well the model is doing relative to an individual person. So we know that some individuals will match the panel mean and some will be off by some degree. We want to see on average how well the model does relative to an individual. So the first thing that we want to do just to sort of calibrate ourselves, we now are taking a molecule and we're collecting 55 numbers for it, one for each label. And then we give the same molecule to the same subjects again, and they rate it again. And we look at how the panel rates the first one and the second one. And we use this metric of cosine similarity just to measure how similar they are. And we can see that test-retest is somewhere around 0.78 in this case. And so that's an anchor for us just to understand this cosine similarity metric. We can also take our data and shuffle it. So now I take all the ratings of my subjects and I randomly assign them to new molecules. So I break any correlation between molecular structure and perception, and I plot that, and it looks like this for cosine distance. And so now you can see sort of the endpoints that we're looking at, and we want to see now how one rater looks in this. So if you take one panelist from this, how well do they match this panel mean that is the sort of global view, average view of what this smells like. And so when we do this across all odors and all different subjects, all different panelists, we can see that cosine distance here. This is on some cases, the person matches the panel mean very accurately up here. In some cases, they do very poorly. And on average, they fall around this level. If we now do the same thing, except we take two people and average them together, this gets better, right? So now you're averaging across individual differences, so you have less noise, and the number rises. And we can repeat this for different panel sizes. As we increase the panel size, we get closer and closer to this test-retest value. We get closer and closer to this mean value of what the panel thinks this smells like. So the question is now, where does the model fall on this scale? And so we take the graph neural network predictions and plot them in here, and we find that they fall between 2 raters and 3 raters. So also interesting to note here, right? First of all, we are at sort of superhuman performance, right? So if you took one panelist off or 2 panelists off your panel and replaced them with this model, you would be doing better. Second, this model has sort of a narrower range of noise on it. So it never does a particularly amazing job at this task. It also never does or rarely does a particularly poor job at this task. It has a much tighter range on this. So just to show you briefly at the sort of single molecule level what this looks like, in orange here is the panel consensus. This molecule smells smoky and medicinal. And in blue is the prediction from the graph neural network. Of course, there are 53 other labels I'm not showing you. They're all about 0 in this case. So the vast majority of our data, the labels fall around 0. Usually most molecules have a relatively small number of positive values here. It's very, very sparse data. Here are 2 more examples. Again, in orange is the panel consensus, and it's blue is the graph neural network prediction. And you can see that the graph neural network is making quite good predictions in this case. So our model now can achieve the superhuman performance on characterizing odors. We see that the graph neural network is closer to this panel mean than an individual panelist is. And that is true about 60% of the time. And I also want to point out that this model has never actually smelled the molecule, right? Each individual is actually allowed to take the molecule, smell it, and report what it smells like. The model is just looking at molecular structure and is beating individuals at this task. Okay, so now we'd like to see, go back to sort of a broader question. I talked about how this graph neural network can learn a different odor representation. Here I'm going back to a sort of color analogy. There are basically color spaces that allow you to map different stimuli in this perceptual space. And what we'd like to do is figure out what are the axes of this space so that we can make some sort of odor classification system. So instead of hue, saturation, and brightness, what would the axes be labeled in olfaction? And just to remind you, we can sort of take this middle layer out of the neural network and try to use that as a metric for this. And when we do that, we see that, we can see a couple different things. One is that maybe what happened is that this neural network learned the specific task really well, how to do that task, but it doesn't generalize to other tasks. Or maybe what it's learning is some sort of general representation, some general axis of odor space, and that allows us to do well on other problems. And what we see is the latter. If we compare this to the dream olfaction task and we take this representation out of it and try to learn how well, just apply this to the previous task, we can see that, again, above the line suggests that the GNN is doing better. Here, we're just taking these embeddings out and using a simple random forest model, and we outperform the previous gold standard in the field that was tuned to solve this problem. We can also look at the Dravnik's odor atlas and see comparison here. And again, for the labels in this particular odor atlas, the graph neural networks embedding is really letting us outperform previous best methods. So the other thing that we're interested in is going back to these cell triplets. If we have a real method of looking at odor space that sort of smoothly understands what's going on in that space, we'll no longer have these activity cliffs that we've seen before. So again, just to remind you, we have a sort of an anchor molecule here. If you look for molecules that are structurally very distant from it, but smell the same, you'll go in this direction. And if you're looking at things that are perceptually very different from it, but structurally very similar, you'll go in this direction. So these two molecules have very minor structural differences, but very large perceptual differences and vice versa. We can now use this model to actually plot these. So we can use structural distance, which in this case is the Tanimoto distance, which is a standard in the pharmaceutical field. And we can, for each molecule, make a plot like this and set some thresholds. Things that are in the sort of lower left and upper right quadrant, where as you increase structural distance, you also increase perceptual distance, are not very exciting. This is what we would expect. But if you look in the upper left and the lower right quadrants, it means that the model's representation is understanding something more than just simple structural similarity here. And when we do this, we can actually find sort of novel cell triplets. So here's one example that the model spits out for us. This molecule smells fatty. It's structurally quite similar to this molecule, but the odor is quite dissimilar. This molecule is very structurally dissimilar from it, but also has a similar characteristic. So in summary, first of all, we characterize the odor of 400 novel molecules. This data set has quantitative ratings for 55 different labels with high test-retest and can be used for a lot of purposes besides this model validation that we've done here. It can be used to train other models. Second, our model outperformed our best human panelists when they were asked to describe the average panel perception of an odor. And third, the graph neural network really learned an odor representation that bridges these structural activity cliffs and can generalize to novel tasks. Finally, I want to thank the lab. Lots of people contributed to this. It was a large data collection effort. Specifically want to mention Emily Mayhew, who was the postdoc who led this project. And I'm happy to take any questions.